All right. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for the week completed almost. Help us to glorify you what we do this day and just to learn a little bit more about linear algebra, Lord. In your name I pray, Lord Jesus. Amen. All right, so I did horrible injustice to the theory of dimension last time, but I at least showed you that clean proofs can be given, even if they aren't presented in class. And so that brings us to section 2.6 in my notes, which is on coordinate mappings. So we're going to talk about coordinates today. And start with a proposition. So this is proposition 2.6.1 in my notes as they're currently existing. And so we have a vector space over a field F, and we have S is a subset of the vector space. Then S is a linearly independent excuse me, set of vectors if and only if for any finite list of vectors. All right. We have the property that if there exist A1, AK, and B1, BK in the field, such that A1, V1 plus plus AK, VK equals to B1, V1 plus plus BK, VK, then A1 equals to B1 on down to AK equals to BK. In other words, if S allows equating coefficients of any finite subset, then S is linearly independent. All right. It looks so innocent in my notes, and then I try to write it out. Such a drag. All right, so let us go with the forward implication here. I'll try to put it in here, proof. So let's see here. Suppose S is linearly independent and V1 through VK are in S, and A1 V1 plus plus AK VK is equal to B1 V1 plus plus BK VK. I'd like to prove that A1 has to equal to B1 and so forth on down the line. So what can I do? My goal at the moment is to show that this implication holds, right? I want to show that this necessarily follows from the data I have. How should I get to that? Yeah?
Could we write each coefficient as the sum of two coefficients for, like, if we have basically C1 V1 plus C2 V2 plus
Uh-huh.
dot 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 B C2 K VK going up for certain C's that equals 0.
Yeah.
With all the C's being 0. Might not have been.
No, I think you got the right idea. So how do we make that happen? Like, let's put everything on one side, right? Then we can do what you're saying. See, then we can put the birds of a feather together, right? Let's see here. I'm sorry, I regret saying that. AK minus BK. So this is an algebra class. We should do algebra, right? So I'm using, that we have subtraction and associativity of addition. As a general point of order, I don't announce my use of the axiomatics in here because, well, yeah. So then what? Now, we can think of this as like the C1, right? And this is the CK. So by linear independence of S, we have that A1 minus B1 equals to 0 all the way until we get to, AK minus BK equal to 0. Hence what? Hence A1 equals to B1 and AK equals to BK. So that holds for arbitrary K. Okay. So that's the forward implication of this proposition. How about the reverse? So let's suppose S allows equating coefficients. All right, that saves me some writing, doesn't it? Let V1 through VK be elements of S. And suppose C1 V1 plus dot 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 plus CK VK is equal to 0 for some constants in the field, right? Then what? What do we have? We're assuming the equating coefficients property, right? So we need to find some way to equate coefficients. How about this? But, or note if you like, 0 is equal to C1, excuse me, not C1, but it's equal to 0 times V1 plus dot 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 plus 0 times VK, right? In other words, we can think about the C's being the A's and all of the zeros being the B's in my definition. Hence, by equating coefficients, C1 equals to 0, CK is equal to 0 by equating coefficients. Property of S. Thus, S is linearly independent. By the definition, right? Because if we take a linear combination equal to 0, then it has to be the trivial combination. If we can prove that's linear independence, and we have proved that. So we have three kind of really different characterizations of linear independence now, right? The one is that we set C1 V1 plus da 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 plus CK VK equal to 0. It implies all the coefficients are 0, right? The other is that it has this equating coefficients property, yeah? And then the third one is that there's no way to write one of the vectors as a linear combination of the other vectors, right? In other words, there's no linear dependence is how we could define linear independence. As I've told you guys, that third way is only possible because we're working over a field. So Okay, so yeah. Now, so this is important. This is really the foundation of coordinates is very much based on this particular proposition. And if you take a look back at Calculus 2 and start thinking about all the times we equated coefficients in Calc 2, do you guys remember? No? Like example 1, we had something like, 3x plus 2 over, x squared minus 3x plus 2 maybe. And we're like, oh, well, that's a over, x minus 1 plus b over x minus 2, The concept that this a and this b are independent of one another, that is in part because the function 1 over x minus 1 and the function 1 over x minus 2, those are actually linearly independent as functions. So here's a kind of scary question. What's a basis for the set of rational functions over the reals? What's a rational function?
Like a polynomial over
Polynomial over polynomial. That's a good answer. So it is the form, like, I'll use x. P of x over q of x, right? Such that p of x and q of x are elements of, in our current notation, r of x. And there is some fine print here. Q of x is what? Is not identically equal to 0. This means not identically equal to 0. If you'd prefer, I could replace this with the statement q not equal to 0, thinking of q as a function. All right. What's a basis for this? So first of all, notice that R of x is a subspace of V, right? And so if we wanted to, we could start our basis with, a basis for this, which is easily 1x, x squared, so forth and so on, right? That's a choice. The so-called monomial, the monomial basis for the polynomials, you could do that, right? This is monomial basis for polynomials. But that's not enough, right? You also need things of the form like 1 over, x minus a constant. Any choice of constant, you need those, right? And you also have things like this, right? In fact, you have things, generally speaking, like this. And then the other thing that can happen is you can have things of the form things of the form, I guess, alpha x plus beta divided by, say, x minus gamma quantity squared plus delta squared. So-called irreducible terms, right? In the partial fractions decomposition, sometimes we needed those in Calc 2. And you won't find this in Stewart, probably, but in a real calculus book, you'd also find things like powers of these. I believe that if you took the union of these, as well as these, as well as those, that would suffice to give you a basis for rational functions. Yeah.
You could make it even just one general term by saying where A and B are in the complex in general, and then to a power of an integer, whether positive or negative.
Ah, you're absolutely right. If instead of, I mean, I like your idea, but let me trade your idea for a different context, which is if I was looking at like the rational functions over the of a complex variable, then you're absolutely right. I could just use this as a basis for those, because the rational, like polynomials over a complex function, always completely factorize. So yeah, I could just rely on like these guys to build any complex rational. But I do want a real basis, so I kind of stuck with this. But these are, you could prove that these are linearly independent, actually. That's assumed in calculus too, because we just say you can equate coefficients of these terms, and it just always works out. Yeah? But it is true, like this and that are actually linearly independent as functions. You're like, well, isn't one multiple of the other? Well, it is, but what's the multiple? It's not a scalar multiple, it's a function multiple, right? And that's not allowed in the world of linear independence. Anyway, this is not in the notes, it's just something I was thinking about and I want to share with you guys. So every so often I play in here. I'll get back to work. What's this? Oh my goodness. Ah. Ah. The horror. Oh, but there was a point to this. What's the dimension of the rational functions? What's the dimension of the polynomials? Remember, the dimension is what? The cardinality of the basis, right? Yeah, they're both infinite, but they're different, right? So the dimension of these is just aleph naught, right? Whereas the basis, in other words, it's as big as the natural numbers. On the other hand, the rational functions, notice that to get the basis, you have to start throwing in what? Real parameters, right? So that means to index it, you can't do it. I mean, you can't just do it with like numbers. I mean, you can't do it with natural numbers. You need real numbers to index it. In fact, the dimension is going to be what? It's going to be uncountable, right? But it would just be, well, if you believe that sort of thing. So it's the same as the cardinality of the reals. You might say, but wait, you need more than one real constant, right? But only countably many such constants, so it still has cardinality of the reals. See, because I need a countable collection of these and a countable collection of those. So, countable collection of... All right, anyway, I'll shut up. Example 2, actually not an example, definition. If we have beta, v1, v2, vn, aw man. Well, I'm just not listening to my, what have I done? Son of a gun. Well, you know what, I'm just not even going to use this at the moment. So suppose this is our basis, and for v over the field, all right? And x, an element of v has x equals to, I'll use different letters altogether, a1 v1 plus a2 v2 plus plus an vn, right? Then the coordinate vector of x with respect to the beta basis is equal to a1, a2, an. In the notes, I've used f1 through fn as a basis for the vector space, and I've used v1 through vn as the coordinates. It's not wrong, it's just kind of distasteful given other things I've written on the board today. All right. But there really is no, I don't have a fixed notation in here, all right? So like we need to announce what we're doing when we do it. This does have a fixed meaning though. This means the coordinate with respect to basis beta. And it's assumed that this is an ordered list. All right? So here, let me give you an example. All right, so if we had V was, say, A in the 2 by 2 matrices, right? Let me just say V is our 2 by 2, okay? Then we could say beta is E11, E12, E21, E22. That's kind of like the usual choice of basis. There's kind of another natural one though, which is this, perhaps. E11, E21, E12, E22. So let me write out A. Let's suppose it's A, B, C, D, like that, yeah? So that's A, E11, plus B, E12, plus C, E21, plus D, E22. But you see that's also equal to A, E11, plus C, E21, plus B, E12, plus D, E22, because like matrix addition commutes, right? But both of these linear combinations have a direct meaning. So this one right here tells me that the coordinate vector of A with respect to the beta basis is A, B, C, D, right? And this one tells me that the coordinate vector of A with respect to the gamma basis is A, C, B, D. See, beta and gamma, they're both bases for the 2 by 2 matrices. They have the same set of vectors in them, but in a different order. The order matters. It has to matter because, you know, it informs which coefficient goes where. This is all built on the bedrock of that proposition, right? If I can't compare coefficients, I can't be sure that I know what the coordinates are of the vector, right? Like the uniqueness of the coordinate vector is guaranteed by that proposition we proved at the start. And the fact that the basis is assumed to be linearly independent. Here's an example. Ax squared plus bx plus c is 7x squared minus 3x plus 2. This has been with you since maybe like, what, freshman, high school? I don't know. When did you guys learn this? So what can you tell me about A, B, and C?
7, -3, and 2.
Right, what are you using?
Linear independence.
You are using linear independence of monomial basis. You are. And so what that means is if I say like P3R has beta equal to, oh, I don't know, x1 x squared, because I'm weird, then, you know, if I call this thing V, what's the coordinate vectors of V equal to in this case?
-3, 2, 7.
Very good. This seems too easy. Let's make something harder. Yes, no? All right, what else do I got to show you guys? Something. So finding the basis and finding the coordinate map for different subspaces generally requires calculation, right? Some of these easier examples, we can just kind of like, we don't really need to do much calculation, right? Like the standard basis. What's the coordinate vector with respect to the standard basis for a vector? The vector itself is the right answer, that's right. So that's kind of simple, right? If we talk about v equal to fn and beta equal to e1 through en, then if x is an element of v, then the coordinate vector of x with respect to beta is literally just x again. But generally speaking, that's pretty much the only time that happens, right? Otherwise, we need to think through it, and we need to figure out what actually the coordinate vector is. All right. But this much is true. No matter how abstract the vector space is, right, the coordinate vector is always just a column vector. Am I right? I'm not right. This is false, because your vector space could be infinite dimensional, in which case the column vectors, infinite dimensional column vectors, we don't really have. Unless we're Russian, then they like to talk about them. But outside Russian mathematics, not so much. I don't know. So if your concept of column vectors is finite column vectors, then certainly that's only good for finite dimensional vector spaces. For infinite dimensional spaces, there is a notion of coordinate vectors, which I'll show you at the end of class. But I don't know if I even invented one homework problem for you guys, because I haven't. My brother says they're useless, and I want to prove him wrong, but I haven't found it yet. So I did something. Another example, which is sometimes nice, is like calculus-based. So let's kind of play with one of those. So this is the standard basis. Of course, if you have fm by n, right, and you let beta be, eij, such that 1 less than or equal to I less than or equal to j, and j less than to me, m, 1 less than or equal to j less than or equal to n. This is, of course, the basis of the unit matrices. But this begs some questions, right? Like they already begged my last example. What's the ordering that's given here? So I think generally speaking, people either use a row ordering or a column ordering. They either order them row by row by row by row down, like I did with beta over there, or column by column, like I did with gamma. Those are kind of the two standard choices. So I don't think I make a choice, so it's ambiguous, but I'm sorry. I'm just saying you'd need to pick an ordering if you were going to do calculations in this, yeah? Okay. All right, so where am I? Example 4? 4, yeah. How about this? What if we have f of t equal to a t cubed plus bt squared plus ct plus, well, I guess I'll use e. And let my basis be 1, comma, t minus 1, t minus 1 squared, t minus 1 cubed, right? For P4 over the R, right? Let's find the coordinate vector of f of t. How would we do it? How about this? Calculus 2. Calculus 2 says that we can write f of t as the sum n equals 0 to infinity of the nth derivative evaluated at 1 over n factorial times t minus 1 to the power n. Specifically, that's f of 1 plus f prime of 1 times t minus 1 plus 1/2 f prime prime of 1 times t minus 1 squared plus 1/6 third derivative of f evaluated at 1 times t minus 1 cubed. So all I need to do is calculate those derivatives, plug in 1, I've got the coordinates. So like f of 1 is a plus b plus c plus d. Yep. Oh, my bad. I used e, didn't I? Weirdo. Me, not you. What's f prime? Okay, f prime prime.
16t plus 2b.
F prime prime prime.
6a plus t.
No. Right. You got it. So we've got f prime of 1 is apparently just 3a plus 2b plus c times t minus 1. And then 1/2 f prime prime of 1. So I got a 3a plus b there. I divided by 2 times t minus 1 squared. And then that's going to work out to a times t minus 1 cubed. So, hooray! This, and that are the coordinates. The coordinates of f of t with respect to the beta basis are a plus b plus c plus e, and then you got your 3a plus 2b plus c, 3a plus b, and a. Who says I never do hard examples in class? Haha. I mean, this isn't that hard if you use calculus. But if you don't use calculus, this takes longer. Right? Well, it'll take longer for me, at least. So don't forget, Taylor's theorem is a useful tool for polynomial examples in linear algebra. Especially if you've got a monomial basis which is like shifted like this. I would say that's a shifted monomial basis. Another example, there are various examples in the notes. I won't do all of them. Let's look at this one maybe. Shifting gears example-wise a bit. Example 5. So let's talk about the complex numbers. Complex numbers over C have basis, we could use 1, right? If you did that, then if you think about z is equal to z times 1, so the coordinate vector, so if my basis is just the number 1, this is exceedingly silly, but the coordinate vector of z is, well, z. Stupid. On the other hand, if we look at the complex as a vector space over the reals, we have basis beta equal to, say, 1 and then I. And then if we have z is equal to x plus iy, then the coordinate vector of z with respect to that basis would be xy. I mean, you could be weird with the first example. Like, what happens if we put gamma equal to, like, I? Then if I pick z, I have to do, like, I times z over I, right? So that tells me that my coordinate with respect to the beta, with the gamma basis for here would be z over I, which would be dumb, but you could do it. Just like in the complex over the reals, you could let your basis gamma be like I1 if you wanted. Then your coordinate vector of z with respect to that basis would be what?
Y over H.
Very good. Yeah. You got it. All right. And in the notes, I have like a similar example for 2x2 matrices, but I'll let you read that. So, what else can I tell you here? Sometimes we're interested in calculating the basis for you know, like a particular set of a subspace that we know and love, right? So like, so example 6, if we have A, an element of f m by n, right? Then we can talk about the column space of A, right? That's a subspace of Fn. And we can talk about the row space of A. That's a subspace of F1 by M. And we can talk about the null space of A. I think I got that wrong, which is a subspace of Fn. What was column space is what? For an M by N matrix, where does the column space live?
1 by n? No.
It's not N there. I should have an M. For example, if I have like a 2 by 3 matrix, each column is a 2 vector. So the column space is a subspace of like 2-dimensional space, not 3. So the question then is, for column space, row space, null space, how do you find a basis for these? Yep.
Should row space be 1 by n?
Ah, yes, thank you. Excellent. Muchas gracias. All right, so we have well-known calculational procedures for finding the basis for each one of these. I don't cover the row one in my 221 course, but Majeric might have in his. What have they done? I know, right? There we go. Sorry, YouTube. Because you know I'm not editing that. All right, so so simply put, if we calculate the reduced row echelon form of A, right? If you calculate that, you calculate this, calculate it, right? And step number 2, the pivot columns of A give basis for column space of A. And the pivot rows of A give basis for the row space of A. And then the null space is a calculation, right? So just to, you know, be a little bit more specific here, I probably should get out the projector and look at one, right? Here, let me get it out. You guys got it? Okay. Oh man, I know, we never have enough time in here. Although I always feel better when I remember class ends at 4:05, not 4. It's like there's a moment of like, oh man, I've got 6 minutes left. Then I'm like, oh wait a minute, oh man, I've got 11 minutes left. It's not quite as bad, right? Let's see here. I think I got enough tabs open. Let's see here. Haha, found it.
Looks like you could spell out a message from all the tabs. Order them correctly.
Let's see here. So in the notes, I have all kinds of exciting things like, you know. So, I do have a little comment here, the lexicographical ordering, which goes row by row. So lexicographical is the row by row. And I guess that's going to be that's my choice. That's my standard definition for the ordering of the matrix units in here. I forgot that I did that. All right, let's go on here. I mean, example 2.6.8 is a fine example about how to calculate coordinates for like the vector 1, 2, 3 if your basis happens to be what's given there, like E1 plus E2, E2 plus E3, E3 plus E4, and then E4. You do the row reduction, and that tells you I need 1 of the first, I need 1 of the second, I need 2 of the third, I need 2 of the fourth, so my coordinate vector is literally that. So, but then, you know, that's fine. But a lot of times you'll find in here that, you know, you don't actually want to use a row reduction because you want to use like calculus like I just did. It's so much faster, right? So, traditionally I make a snide comment at this point, but he did ask me if he could leave really politely the other day. So I will not make any comment. So here's one. This is a matrix A, and we can ask what's the basis for the column space, right? So it should be it's a you know, column vectors are 3-dimensional here, so we expect you know, a basis for possibly a subspace of R3, and cool. And so what we got. So you know, you calculate the row reduction, and we did that last semester, so I don't need to do it anymore. Woohoo! And I love having 221 as a prerequisite. It's so freeing in here. It's just it's amazing to not spend the whole semester row reducing. It's just fantastic. So we get that, right? And that means that the pivot columns are the first, the second, and the fourth, right? The third one can actually be obtained by 5/3 of the first column plus 2/3 of the second column by the column correspondence property. As I show down here, column 3 is actually 5/3 column 1 plus 2/3 column 2. So a basis for this matrix would simply be the first column, the second column, and the fourth column. That would be a basis for column space. This would be a very stupid test question though, because since there's 3 things in the basis, you can literally choose any set of 3 linearly independent vectors and it serves as a basis for the column space, because the column space here is R3 if we're working over R. Hey. But the null space here is interesting, right? So let's talk about that. How would you calculate the basis for the null space here? The row space also is, so here's the theorem. The dimension of the row space and the dimension of the column space are equal. See, because like the algorithm I gave you here, pivot rows give you a basis, pivot columns give you a basis for row space and column space respectively, right? So same number, same dimension. So we can either define the rank of a matrix as the dimension of the column space or the dimension of the row space. Either way we agree. The null space though, it's not manifest. Like you can't just read null space straight off the matrix, right? We have to do that little calculation to figure that out. So here, let's see if we can figure it out. We've got what? If we look at AX equal to 0, X is a 4-component vector, right? So I've got like X1 is minus 5/3, X3, X2 is minus 2/3 X3, right? X3 is X3, X4 equals to what? Oh, 0. So that means that X can be written in the form like minus 5t, minus 2t, 3t, 0, which is t times minus 5, minus 2, 3, 0. So null space is the span of minus 5, minus 2, 3, and 0. You see what I did? I said X3 equal to 3t, right? To get rid of my fractions. And you can check this quickly, right? Does this vector times the matrix give you 0? It should. If it doesn't, I miscalculated something. And this also checks with the rank nullity theorem, right? The dimension of the column space plus the dimension of the null space should be equal to the number of columns in the matrix. We had 3 plus 1 is 4. Come Come on. Don't do this to me. Still got things to say today. All right. So, and I think you guys, I hope you guys know the null space calculation. Obviously it matters. These are, I think, proofs of some of the things I just said, more or less. And some examples of like these sorts of things. I wanted to get, so here's a sort of a general sketch of the proof of how you calculate the null space basis and why it is how it is. Here's another example, like the null space of 1, 2, 3, 4. This makes a great test question because it's really simple, but it will destroy students who don't know what's going on. It's very easy to grade this question, but anyway, so if the matrix is 1, 2, 3, 4, then the row reduction of A is, there's nothing to do, it's done, it's already reduced, right? the pivot column here is the first entry, boop, E1, it's one dimensional. And so all I can do is, write x1 in terms of 2, 3, and 4 parameters, which gives me this, and then I factor the 2, the 3, the 4 out to get this, that, and that. And these three vectors are perpendicular, whatever that means, to that row vector, 1, 2, 3, 4. And so the basis for the null space here is three-dimensional, and these are the three. So this is actually a very nice example because of its simplicity. It's maybe, it'd probably be less confusing if I did it for like a 2x4 matrix, right? Like there's something a little bit unsettling about doing it for a 1x4, but there it is. Here's an example for a null space of a 3x5, and because there are three pivot columns, the null space is two-dimensional. 3 plus 2 is 5, not an accident. This one's also a nice example because it's really easy, right? So the row reductions obviously just gives you the first row because the second two are the same. And notice it's quite obvious here that the dimension of row space is 1, and also that the dimension of column space is 1. That's just manifest from this, right? Because it's just the same row and column repeated. And anyway, right. So how do you define coordinates for an infinite dimensional vector space? Well, you use functions that are called characteristic functions. And basically the way it works is you define a function such that it's 1 when you input the vector and it's 0 otherwise. And if you think about it, if you got a basis for your infinite dimensional space, you just define the coordinate vector like using that. So if if you plug in the basis vector, it gives you 1. If you don't, that coordinate map gives you 0. And so you can build, so any vector in the vector space is built from a linear combination of basis vectors, right, finitely many. Correspondingly, there's finitely many of these coordinate functions that are 1 when you input the vector and non-zero otherwise. Anyway, so these kinds of functions give you a way to construct these infinite coordinates. But yeah, and I prove here that they have the properties that you'd like. But like I said, I haven't been able to really come up with a very, all I'm telling you here is that there is a notion of coordinate vector for infinite dimensional space, but it's also kind of like, on the one hand, so simple it's stupid. On the other hand, so like simple it's useless. These characteristic functions also come up in some other abstract parts of math. Like a characteristic function is simply a function on a set, which is like 1 if something's in the set, and it's 0 if it's not. So like this is the idea of a characteristic function. Anyway, let me stop talking about that. What remains here is a proof that the dimension of a finite dimensional vector space is equal to just one thing. If it is a finite vector space, if I take any two bases in a finite dimensional vector space, they must have the same number of elements. The proof I gave you last time rested on a bunch of things involving Zorn's lemma and transfinite, arithmetic and stuff. This example is straight calculational. This proof is straight calculational, involves the trace. So let me explain the proof how it goes. So what I do is I take two bases, one with n things in it and the other with p things in it. See, n, p. And what I do is I simply expand the kth basis element in terms of the other basis. Likewise, I expand the jth basis element in terms of the other basis. And I introduce coefficients here for that sum. And then if you plug the one into the other and you equate coefficients, as we can do because they're linearly independent, you end up with the relation going down here. You end up with a relation that this is equal to 1. But if you look at this, this is matrix multiplication. If you focus on the outside indices, like 1, 1, 2, 2, all the way to nn, that's the 1, 1 component of a matrix. And going on here, if you look at it, you can eventually see that the product of these two matrices is equal to the identity matrix because you get ones and zeros as appropriate. And so just collecting it all together, it gives me on the one hand, the matrix C times the matrix D is IP, but on the flip side, by the same argument, D times C is IN. All right? But you can, if you have that, you can take the trace of this, both equations, right? The trace of CD is equal to the trace of IP. What's the trace of the P by P identity? Just P, right? 1 plus 1 plus 1 P full times is P. What's the trace of the N by N identity? It's N, right? But you guys proved in the homework, I think, I haven't graded it yet, that the trace of C times D is the trace of D times C. P equals N. So this is a constructive, non-inductive proof that the dimension is equal if you have two different bases of the same finite dimensional vector space. So I'm fond of this argument. It's part of the reason I make you guys prove the trace of AB is the trace of A, trace of BA. Anyway, next time we will be doing what? Oh, theory of subspaces, I think. Is that right? What's that? Oh, something about a quiz. I think I don't remember. I remember. Although I don't have my schedule in here. Rats. Anyway, I hope you guys have a good weekend.